Hello everyone, my name is Joanna Chi and I am from Simon Fraser University. Today I will be presenting DZiG, Sparsity-Aware Incremental Processing of Streaming Graphs. This is a joint work done with my lab mate Mugilan Mariappan and our advisor Keval Vora. Graphs are a flexible data structure that can be used to easily represent a variety of data and are applicable to many situations. We can use graphs to represent social networks, roads, and even disease transmissions. With these varied applications, graphs can also be very large in size, with millions of vertices and billions of edges. As a result, it is important to have systems that can scalably and efficiently process large graph data. Graphs are also dynamic and they naturally evolve over time as the data changes and grows. So we have streaming graph processing, where graph computations are run continuously in order to provide results that reflect the current state of the graph. For these graphs, being able to return results in a timely manner is important, as stale results may no longer be useful. So as time continues, the graph receives more and more updates via a continuous stream of graph mutations. And then the query results are computed on the latest result of the graph, which contains all the previous updates. Thus, it is important to be able to compute results at a low latency. To provide timely results, streaming graph processing uses incremental processing that reuses work that has already been done before, so that it does not redo the same work again. This means, as updates are performed on the graph structure, the computed results are incrementally refined to reflect the impact of these updates. The goal of incremental processing is to reuse the work that has previously been completed, so that processing will only be done on vertices that are affected by the graph changes. Graphbone is a state-of-the-art streaming graph processing system that does incremental processing to quickly compute final results that are fully correct. This means the final results are the same as if you were to perform a from-scratch BSP execution on the updated graph snapshot. Graphbone tracks dependencies in form of intermediate vertex values as computation progresses, and then it performs dependency-driven incremental refinement that incrementally adjusts these tracked values. So let me quickly explain Graphbone's dependency-driven incremental refinement. Basically, we first identify the change in vertex values that happen as a result of graph mutations, and then we propagate these value changes to the outgoing neighbors in a stepwise fashion across iterations. In this example, we have the vertices u, v, and w, and I am showing how their values change across consecutive iterations, from iteration k to iteration k plus 3. The colors represent the values of vertices that are computed by the algorithm. So if the color is different across consecutive iterations, for example u here, going from maroon to red, then that means the value of u is different in those two iterations. So now, the whole point is to incrementally adjust these values when the graph gets updated. This is done by propagating changes or differences in values that result from the graph update. So here, first u and w receive changes from the updated graph and calculate new values for themselves, and then, because their values change, they push their changes to v during the next iteration. And then, based on these changes, v calculates its new value. Now during this iteration, u and w once again receive new values from their neighbors, and so they recompute the results and once again push their values to v. This process continues iteratively till final results are computed. Now an interesting thing to observe here is what happens when the changes start diminishing and the values start to stabilize. So here, only w's value changes in iteration k plus 2, but u's value remains the same, which is shown by the same light yellow color here. So w sends this change to v, which is fine, but v's value at iteration k plus 3 is not aware of u's value from iteration k plus 1. So in order for v to calculate its value correctly, it still needs to continue pushing its value to v. So this is unnecessary work that needs to be done, which causes more values to be propagated even when changes have diminished and values have stabilized. The issue here is that the vertices do not retain the changes that they received in the previous iterations. So here, even if v had received this change in the previous iteration, it did not retain this change in the next iteration, which forces u to resend the value. Processing changes in this manner is not friendly to computation sparsity. We measured the effect of this issue by profiling the time taken and work done as iterations progress. So in the plot, The x-axis is the number of iterations as execution progresses, while the left y-axis is the iteration time, which is shown by the line points here. The right y-axis indicates the number of edges processed in each iteration, and this is shown as bars here. So with GraphBult's dependency-driven incremental refinement, the time taken in each individual iteration increases, and this is mainly because the number of edges that get processed increases, since the stabilized values need to be propagated in the rest of the iterations. In comparison, if we look at incremental execution that simply restarts from scratch, which I am showing here as a blue line and gray bars, which I am calling resync here, we can see that it is successful in retaining computation sparsity in later iterations. In fact, even though restarting from scratch is much slower than GraphBult, the later iterations with restarting from scratch take lesser time per iteration than dependency-driven incremental processing in GraphBult. To leverage this difference in performance, strategies like hybrid execution switch the execution from using a dependency-driven incremental refinement to the baseline BSP execution. However, this means that these strategies are fundamentally giving up on using dependency-driven incremental processing once computation becomes sparse. So then, this begs the question, how can we retain high-performance execution with dependency-driven incremental processing during sparse computations? To address this, we developed DZiG. DZiG is a sparsity-aware incremental refinement technique that uses dependency-driven incremental processing while retaining high efficiency in the presence of sparse computations. DZiG also follows the same philosophy of GraphBult, where dependencies are tracked as iterations progress, and the dependencies are then incrementally refined when the graph structure is mutated. So there are two things we need to figure out: how to identify sparse computations and how to retain computation sparsity as we perform incremental refinement. We first define sparse updates, which we call Delzero. Delzero is defined as the delta between a vertex's value across consecutive iterations. Basically, if the change in value, or delta, is less than the algorithm's applied epsilon, then that change is a Delzero. In our previous example, we can see that vertex u in iteration k plus 2 does not have a new value, so the delta for vertex u is a Delzero because there is no change, and hence, u does not need to push any value to v. These Delzeros are usually naturally expressed in graph algorithms to identify whether vertex values have stabilized. For example, in the Pagerank algorithm, after the vertex value is computed, it is compared with the old value to see if the difference is above a threshold. This comparison directly determines whether the update is a Delzero or not. Now that we have identified sparse computations as Delzeros, let's see how we can retain them. We basically want to make sure that we express the computation in terms of changes across consecutive iterations. That is done by expressing incremental refinement in a recursive fashion. So in these equations, we want to compute g(t) of I, which are the dependencies for the updated graph, using gi values, which are the dependencies from the old graph. This happens recursively, which is captured from the delta ti minus 1 on the right side. Effectively, this means there is an implicit dependency between consecutive values of the same vertex, and this self-dependency retains the changes that were propagated up until the previous iteration. So then, we are only left with changes that happened in the previous iteration, and this is captured by the remaining terms in the equation. So first, there are the direct changes resulting from the edge mutations. For example here, a new edge from G to D is added, so that the old change needs to be propagated from G to D. Similarly, edge B to C is deleted, so we retract the old change that was propagated before the deletion. And then there are the transitive changes that trickle down from these direct changes. So for instance, as D's value changes significantly, the change is sent out to its out neighbors. Now, because all of these changes are based on the previous iteration, we can directly identify Delzeros, which is our sparse updates, and suppress them. And that is captured by the precondition on the operations here. Finally, going back to our original example, we can see that the vertexes u and w once again push their values if and only if their own values have changed. And we can also see that v maintains the change from the previous iteration. So when u's value remains the same, u's value is not sent again, and thus sparsity is retained in the computation. We have a formal proof of correctness, showing that results computed by our Delzero-aware incremental refinement will always be consistent with the baseline BSP execution that starts from scratch. I won't be going through this proof here, but do check out our paper if you are interested. Our Delzero-aware incremental processing retains high performance across all the iterations, even when computations become sparse. So as we can see here now, the time taken in each iteration and the number of edges processed is similar to the baseline BSP execution in the later iterations. But we observe that there is a minor overhead in our D0-aware processing, which becomes visible in the later iterations as the computation reduces. This is because dependency-driven incremental processing does more work per active edge. It retracts the old values and propagates the new values. The from-scratch baseline, on the other hand, just directly propagates the change. So when there are few active edges, this overhead is observed as a minor difference in performance. To avoid this overhead, we develop an adaptive sparse incremental processing strategy that automatically switches the execution to the faster version when these overheads become visible. This is done automatically by monitoring the performance of each iteration and estimating the expected performance using the alternate execution using a simple linear regression model. We found that a linear regression works best in estimating the iteration time, since it is mainly dominated by the number of active edges. Once the estimated value is lower than the actual value, the runtime automatically switches the execution to the traditional incremental processing. At this point, I would like to point out that this adaptive sparse incremental processing and automatic switching is not absolutely required in DZiG, unlike solutions like hybrid execution used in other systems that are necessary for delivering high performance. Our Delzero-aware processing alone delivers high performance, and we are only squeezing out the minor performance difference that arises due to the overheads. There are several other details present in DZiG that I won't be covering in this talk. I have presented the Delzero-aware incremental refinement strategy in DZiG, and I just briefly touched on the adaptive sparse incremental processing. There are also details about dependency tracking and our efficient dynamic data structure based on adjacency lists that enable fast graph mutation. All these details are present in the paper. But I would like to briefly talk about the programming model, which will also show how Delzeros get expressed in the runtime. Here I am showing how weighted PageRank can be easily expressed on DZiG. In PageRank, the rank value is adjusted by weight and sent out on the edges, which is aggregated on the destination by summing the incoming values. So the value changes on vertices and edges are captured by the vertex change and edge change methods. And then these changes are propagated or retracted using the add change and remove change, which basically do an addition or a subtraction on the target value. Finally, the aggregated value is used to compute the new PageRank value for that iteration. Now with this new value, the difference is checked to see if it is a Delzero or not. This is done by the notDelzero function. If this function returns false, the runtime understands that this is a sparse update, and it does not propagate this update in the next iteration. One interesting optimization our programming model enables is merging the propagation and retraction of values on the same edge for faster execution. So when the aggregation function is simple, just like here in PageRank, where it does addition and subtraction, these functions can be merged into a single function called add-remove-change, which directly propagates the difference between the changes instead of sending it out in two steps. We observed that this simple optimization was useful for PageRank, where it boosted performance by up to 40%. Coming to the evaluation, we thoroughly evaluated DZiG across different synchronous graph processing benchmarks: PageRank, belief propagation, collaborative filtering, code training expectation maximization, and label propagation. And we ran these algorithms on multiple input graphs going all the way up to 6.6 billion edges, and we conducted the experiments on a 32-core server. Here I am showing the execution times in seconds across all 5 benchmarks when 1,000 edge mutations are applied. First, we compare DZig's performance with ResInc. ResInc basically restarts execution upon graph mutation and performs incremental computation. Here, as expected, DZiG significantly outperforms ResInc by being up to 133 times faster. Next, we have GraphBolt. Recall that GraphBolt relies on hybrid execution that turns off dependency-driven processing, and its performance is sensitive to when the switch happens. The detailed numbers for different static configurations for GraphBolt are present in the paper, and here I am only showing the best hand-picked numbers where the switch results in the fastest execution. In comparison, DZig's performance is consistent and it ends up being up to 5 times faster than GraphBolt. This is mainly because DZiG ends up processing lesser edges as it successfully maintains computation sparsity. Note that these performance numbers are for DZiG without the adaptive processing model, so the performance gains are purely because of Delzero-aware incremental processing. If adaptive processing model is turned on, DZig's numbers will be even better. We also measured the performance across different mutation batch sizes. So apart from a single edge mutation, we simultaneously applied multiple edge mutations all the way up to 100 million edge mutations at a time. As we can see, Delzero-aware processing retains high performance even across very large mutation batch sizes. In fact, it pushes the scale of dependency-driven incremental refinement to over 10 million simultaneous mutations. When we enable adaptive sparse incremental processing, which is shown here with DZiG AE, the performance improves marginally, except for large batch sizes where the difference in performance is visible. For instance, in collaborative filtering, adaptive processing is noticeably improves DZig's performance for 100 million mutations. The consistent high performance delivered by DZiG is visible when compared with GraphBolt across different configurations. For instance, GraphBolt's dependency-driven execution works well for up to 1,000 to 1 million mutations depending on the graph algorithm. Finally, we compare the performance of DZiG with other streaming graph processing solutions, including Aspen, Graph1, Llama, and Stinger on PageRank and shortest path benchmark. Since these systems focus only on graph mutation times, they do not have any incremental processing support like GraphBolt or DZiG. So here, I am also showing the execution times separately for the graph mutation phase and the analytics phase. When it comes to end-to-end processing, incremental processing in the analytics phase is much more important than just graph mutation, and that's why DZiG and GraphBolt significantly outperform all of these systems. Specifically, in end-to-end processing in DZiG is about 30 times faster than Aspen and 120 times faster than Graph1. When it comes to graph mutation times, DZig's dynamic graph data structure enables fast graph mutation and is competitive with modern solutions. In fact, for a large number of simultaneous mutations, DZig's data structure is actually much faster than recent works like Graph1. There are also plenty of other experiments that I haven't covered in my talk. For instance, we studied the performance across different degrees of sensitivity to changes and the memory consumption by our dependency tracking mechanism. I would highly encourage you to check out our paper for these details. To conclude, dependency-driven incremental processing is important to maintain high performance while processing streaming graphs, and GraphBolt already took a large step in this direction. DZiG takes the next big leap in pushing the scale of dependency-driven incremental processing to high mutation rates, and it does so using its Delzero-aware incremental refinement strategy. DZiG also incorporates important techniques like adaptive incremental processing, merged edge updates, and efficient dynamic graph data structures that enable it to deliver high end-to-end performance and significantly outperform the state-of-the-art solutions. DZiG is implemented in GraphBolt as its core engine and is open sourced under the same GitHub repository. We invite you to check it out. Thank you!